So when we talk about energy, we're only going to really concentrate on two different types of energy. Now, inside the energy, inside each one of these, kinetic and potential, there are different forms of kinetic and there are different forms of potential. For kinetic, we have this vibrational kinetic energy, we have a rotational kinetic energy, and we have a linear kinetic energy. But dealing with a molecule, we're not looking at one molecule and we're not measuring it. We're saying, alright, so we've got a molecule, and we got all the molecules brothers and sisters, the billions of molecules that make up this gas or whatever it is. So we're not going to be concerning ourselves that much with the rotational. We're not going to be concerning ourselves with linear. We're just going to give it a bulk category of kinetic energy. So remember that when we talk about kinetic energy, it's a representation of the average temperature of a particle. So when we talk about average temperature, or when we talk about kinetic energy, we're actually looking at the average amount. Okay. So that's what we're going to talk about, kinetic energy. The other one is potential energy. Now, when we talk about potential energy and we're talking about atomics, molecular and atomic particles, we can be talking about several different types of potential. Nuclear energy is in there. We talk about the binds in there, the weak, the strong, they're all in there. The electromagnetic is in there. Not so much gravitational. Gravitational energy, if you think about the mass values that you're talking about, there's very little gravitational energy there, which is wonderful. Allows gases to be relatively unaffected by the force of gravity, but it's just not that important. So we're talking nuclear potentials, we're talking electrostatic potentials, we're talking about that kind of potential energy. We're not talking about gravitational potential, we're not talking about spring potential. It's just not really there. Okay, cool. So the first one we want to start off with is we want to talk about plasma. It turns out that plasma typically exists, at least the type of plasma that we like to deal with is tremendously high energy, has an awful lot of energy to offer. I mean, the sun is made of plasma for the most part. So it's really, really high. This is high energy. And when we talk about high energy, we're going to be focusing primarily on the kinetic energy. So when we talk about plasma, there's a tremendous amount of high kinetic energy. The temperatures that are associated with particles that are in the state of plasma is really, really high. And that's why some people are talking about the next generations of artillery as being a plasma-based weapon. That you fire these big bolts of high energy particles and drop it on a village and it just liquefies things. Okay, so tremendously high energy particles, but zero potential energy. And because it has no bond with anything, I mean, there's still nuclear bonds that are going on. Protons are still bonded with neutrons in plasma, but there's no other interaction between any other particle in plasma. I mean, those particles are going so fast they don't even recognize anything else in the universe. They're just got tremendous amounts of energy, and even to the point where their potential energy is not even recognizing the electrostatic energy between the nucleus and the electron. The electron is gone. It's somewhere else. Okay, so that's plasma energy. So now moving on to gases. Well, gases is a high energy, but not as high. It's one step below the high energy system. Gases have less kinetic energy. They don't reach temperatures like you get with plasma. Okay, or at least for that particular type of particle. I mean, plasma for hydrogen is pretty high, or plasma, or something else, the plasma is going to be considerably less. But high energy, but not as high. Liquids are solid, our gases are still high energy, but they still have that bond from the electron to the nucleus. It still has that tie there, which means that it has potential energy. But here's the real tricky part. It turns out when you look at fields and look at energies associated with fields, that those field forces create zones of negative energy. So gases have low negative energy. Okay? So they have low negative energy. Let me just put in neg instead of that sign. So if I dump heat in, if I dump energy into the system, it's filling up this energy that this gases have. Think about it this way. So if we were to look at a graph, we'll look at the energy associated with a gas. Here's its kinetic energy. Okay, a lot of kinetic energy. Here's its potential energy. Okay, that negative, and this is the 0 point, that negative potential energy is stabilizing the system. It's bringing a bit of stability here. The more negative potential energy you have, the more stable your system is. I mean, when we talk about planetary motion and you talk about astrophysicists, they talk about objects that have high negative potential energy as being a relatively stable object. They're continuing their motion. The Earth has a tremendous amount of negative potential energy in respect to when we talk about the energy between it and the sun, and even it and the rest of the universe. It has a lot of this negative potential energy. So when we talk about gases, it has a little bit of potential energy, and it has a little bit of negative potential energy, and it has a lot of kinetic energy. So when I dump gases in there, when they reach the point where it's about ready to go from gas to plasma, I'm increasing my potential energy. I'm dumping energy into the system, and it's going somewhere. It's not being transferred to the kinetic energy. It's being transferred to the potential energy. I pump a little in there, and my potential energy reaches that 0 point, and then boom, I'm talking plasma. Okay, all of a sudden the potential energy is gone. Well, that means that the electron is gone. It's somewhere else. So you're putting in positive energy to fill in this potential energy hole. Okay, it's a debt. And once that debt is paid off, that electron's gone. Cool? So that's a gas. So high energy kinetic, low negative energy potential. And I mean low as in the magnitude of it. It's pretty small. Okay, moving on to liquids. Well, liquids, it's the same kind of model. It's lower energy. We keep going down and down the kinetic energy chain. Okay, we start off at tremendously high energies, go lower, and go. We're going to just keep going our way down. And as it goes for liquids, it's the same thing. We get a little bit higher negative energy, and I mean higher as in a magnitude. It's bigger, which means that this is our gas model. That's our liquid model. Here's a little bit of energy that you need. That's the bond between the nucleus and the electron, this little chunk here. This little chunk here is some intermolecular bonding, when we got molecules bonding with other molecules, or not intermolecular, molecular bonds. Well, I don't even know. It's molecule to molecule, like van der Waals bonds. So there's a little bit of energy here too. Okay. So in order to get where we need to get, and I should adjust this because my liquids are going to have less kinetic energy than my gases. So when we get to this, when we start dumping energy into the system, what we end up doing is we end up increasing the kinetic energy first, because it's the easiest way to express energy. So once that kinetic energy has reached its maximum point, it starts filling in the potential energy. Okay? Cool? So if we had a gas at this state, and I should erase this, so if we have a gas that has this much kinetic energy, it needs to fill in this window first, which is in effect raising the temperature, because kinetic energy is a representation of the average kinetic energy. So I'm pumping in energy here to increase the kinetic energy of the whatever it is, the gas, to the point where it fills up what it needs for the kinetic energy, and then it starts filling up the potentials. Okay, fills up that potential, and all of a sudden you got plasma. Well, plasma has a higher window for kinetic energy. You fill up this one, and then you fill up this one. Okay, so you're still pumping positive energy in there. So boom, transfer goes up to kinetic, or goes up to plasma. It has a higher window, but I have to fill in this shell first before I'm plasma. Once I filled in this shell here, it says, oh look, I'm in here. I've got the minimum needed kinetic energy for plasma, and I've got my potential energy. So it fills in that kinetic energy and it's like, oh, ready to jump, starts filling that in. Okay, so that's what's going on there. I kind of screwed up. I didn't mean plasma. I mean, we're going liquids to gases, then gases to plasma, where plasma is the fill up here, liquids is the fill up here, gases are the fill up here. Okay, so sorry about that. Once you've gotten to this point, you're just dumping energy into kinetic. It keeps getting hotter and hotter and hotter. It doesn't, I mean, it reaches a point where it just can't absorb enough energy, but that's what's going on there. So going down the chain, we go down to solids. Solids have very little kinetic energy. You're looking at the kinetic energy, you're looking at solids being something right here, liquids being something right here. So there's very little kinetic energy inside of a solid. Most of the kinetic energy inside of a solid is vibrational. You're getting atoms and molecules vibrating, that sort of stuff. That's where your kinetic energy is typically located, is in that vibrations. Very little rotational, very little translational. So very, very low kinetic energy, not a lot of it floating around, but tremendously high potential. That potential energy is tremendously high. So you got to fill in a hell of a lot of potential energy to jump up to the next state. So you got to fill in your little kinetic, and then you got to fill in your potential, and then boom, you're on to the next one to fill that one in, and then fill this one in, and then fill that one in, and fill this one in. Okay? So transferring to solids, to liquids, you got to pump in a lot of energy, not only to raise its temperature, but to fill in these potential energy gaps. So to fill in that, okay, and until you fill that in, you're still a solid. Cool. And then the other two, BECs and fermionics, they're keeping track of this. The BEC, Bose-Einstein condensates, and fermionic condensates are all kind of keeping track of the kinetic energy. When that kinetic energy is just a hair above zero, you can have things like BEC being created, which is kind of interesting, because what that really means is that for every solid, for every liquid, for every gas, there's a particular value of the amount of energy that it can store. It's got that heat capacity associated before it starts transforming to the next thing. But when you talk about BECs and fermionics, there is a basement level to the amount of energy. If it gets down to that energy, regardless of its state, it jumps to BEC. So you can have a gas that once you reduce it to a point, it simply jumps to BEC. That's why things like hydrogen is very difficult to turn it into a solid, because hydrogen wants to jump to BEC. Because you got it down to such a small energy level that you're not going to walk around a block of frozen hydrogen. You're going to be walking around with a block of BEC, because it'll jump from that gas to Bose-Einstein condensates. It's that basement level. It says, all right, you've reached this number, this magical number, wherever this is, you're now a Bose-Einstein condensate. Now, Bose-Einstein condensates only happen to particular types of particles, and that's why people tend to throw it out there as not necessarily a phase of matter, because not every piece of matter can achieve a BEC. Just like not every phase of matter can form fermionic condensates. But they are phases of matter in that they have their own properties that separate it from everything else. And every particle can achieve this. Every particle is either a boson or a fermion. So everything can achieve it, and that's why it is a phase of matter. Okay? Cool? So that's a quick rundown of the energy states. That's a quick rundown of how energies and this transition from one state to another happens. First of all, you pump in energy, and it increases the kinetic energy until it reaches that threshold. It reaches this point where it's like, all right, as a solid, this is how much kinetic energy I can take. Once I pumped in that much kinetic energy, I start filling in the potential energy. I start increasing that potential energy to the point where it's like, all right, now that I've achieved what I needed for kinetic energy and achieved what I needed for potential energy, I can move on to the next state. So when I move on to the next state, it fills in that kinetic energy first, and then increases the potential energy to a point. Now, when we're increasing the potential energy, we're approaching zero. We've got that negative potential energy that we have to overcome in order to reach zero. Once we reach zero, we're talking plasma. Okay? That's why plasma is zero. Cool. So there's energy transitions.